Hello there. In this video we're going to be working in MATLAB for pretty much the whole entire video in order to implement the Newton-Raphson method in order to solve algebraic equations. So if you're not already familiar with the Newton-Raphson method, definitely check out the video that precedes this one on pretty much how it works and a couple things that needs to be known in order to sort of execute this algorithm. So anyway, we're going to be working in MATLAB, so if you haven't already opened up your MATLAB script, definitely create a new script, title it whatever you want. I've titled mine My Newton-Raphson Method, and let's get started. Alright, so the first thing I'm going to do is just clear the console, just in case I have any other things floating around, and I don't want them to mess up what I'm doing. So what I'm going to do is I'm going to create a new function of some single variable, say x, and I'm going to use x squared minus 5 as our example, since that's what we used in our introduction. So remember, the Newton-Raphson method is defined to be equal to the iteration xk plus 1 is equal to xk minus f of xk all over f prime of xk, where x0 is our initial guess, right? So I'm going to define our initial guess to be 3. That's what we used in the initial example, so I'm going to stay consistent here. Now notice we do need to calculate the derivative of our function f at a particular point, and I don't want to use any of MATLAB's programs that are already made, so I'm just going to create my own central difference method. So I'm going to return the derivative central difference, and I'm going to let h be, something small, right? So I'm going to set d is equal to half of 1 over h times f of a plus h minus a minus h. So that's my central difference, assuming that we take in some function f at some point a, right? So this is my central difference approximation for a derivative. Alright, so now that we have everything ready to go, I'm not going to call this x0, actually. I'm going to call this x old. And the reason why I want to do this is because once we do our iterations, we're going to go up to, something like x10 or x50 maybe. And I don't care about values that are too old. So when I calculate x50, the only thing I need to know is x49. x49 only depends on x48. So we can just replace the old with the new and iterate that process, right? So x old is going to be 3, and let's assume that x new is going to be something really large, right? Now, if the difference between x old and x new is really large, that means our method has not converged yet, and we need to continue the iteration a little bit more longer, right? Let's also keep track of the number of iterations for our method. Alright, so when you do not know how long it will take for the method to converge, a while loop typically is the most appropriate thing to do. So what we want to do is we want to continue this process as long as the difference between x old and x new is significantly large, and you can have control over this threshold if you want to, right? You can make that smaller if you want it to be more accurate, right? Alright, so the first thing we need to do is calculate the derivative of our curve. So this is going to be the central difference approximation to our function at the point x old, right? And then x new is going to be equal to x old minus f of x old divided by the difference, which is f prime of x old, right? And then we're going to increase our iteration number, right? Now, once we get down to here, in our first iteration, we need to check. In our initial calculations, we found that x1 was 7/3 under this example, right? So clearly 7/3 is larger than 3, more than this threshold. So that means we need to go back. So we need to replace x old with x new, right? But remember, we do not want to do this on our first iteration, so let's just do a quick if statement. So if n is not equal to 0, then we're going to do this. Right? So that is our scheme. Now, once we have everything working, then we can display all our data, right? So I'm going to display that your value, the value that you are trying to approximate, in this case it's the square root of 5, but I'm not going to write the general case. If you want to, you easily can do that. Is, and then I'm going to do like a num to string display of x new. And what I want to do is I'm going to display 8 decimal points for that expression. Right? Let's see. Oh, where's my single quote? There we go. So that is my approximation. And let's also display the number of iterations that it took to converge for this. So convergence obtained in num to string. There's no decimal points for this. And notice we increase it before we step out, so we need to subtract 1 from that to get a more accurate value. So that's how many iterations that we had. Right, where's my single quote? There we go, period. So let's just give this a quick run through just to see what happens. Okay, cool. So everything works appropriately. So notice that it says the value that you were trying to approximate, in this case is the square root of 5, is 2.23606.798, which, as we know, is the exact value of the square root of 5, at least up through 8 decimal places. And it only took 3 iterations for that to occur, right? So let's assume we want to approximate the square root of 2, right? So just change 5 to 2. Let's make our output appropriate. So this is going to give us the square root of 2 approximation. So in this case we have 1.4142136, and it converged in 4 iterations. 1 more than the square root of 5, but that's no problem. Notice that we did not change our initial guess, so that probably is why, right? You may want to choose probably 2 as your upward bound, since this is definitely, square root of 2 is definitely less than the square root of 4. So probably if we change this to 2, we can get a faster convergence rate. Yeah, 3 iterations. So anyway, that's how you can implore or implement the Newton-Raphson method in MatLab in order to solve algebraic equations. So this will give us one solution to the equation x squared is equal to 2, and you can do the same by changing your initial condition to say -2 to give you the other solution to the equation. Hope you enjoyed.